Lecture 1, Part 3. I'm going to get into a little bit more of the nuances on voltage measurements and referencing. So in other words, taking the potential energy and actually assigning numerical values that have a meaning to them. So if I have a voltage source here represented by the usual uneven bars, I have a potential assigned to the high, and I have a low potential assigned to a different pole. If I ask what's the potential here, namely the actual value of that phi plus, or what is the potential here, namely the phi minus. So if I ask the potentials at a single pole, I'm going to get a very funny look from my boss, because these are actually meaningless questions. The only meaningful question is the difference between the two. So what is the potential here versus the potential at the other pole? And that difference in potential is what we call the voltage. Cat's now happy. The potential of a given device can be measured using a snazzy meter. As an introduction to voltage referencing, I consider two scenarios of combining voltage sources. So in the first case, I put two identical voltage sources in series with one another, connect them plus to minus. So if I look at when I do this, the conducting section between the two voltage sources are set at the same potential. So however I define this, the phi minus of the top is equal to the phi minus at the bottom, phi plus at the bottom. Okay. If I now examine the potential between point A and point B, I have a potential difference of phi plus minus phi minus. If I now look at the potential difference between B and C, I get phi plus minus phi minus again. Again, these are set by the sources. If I look at the potential difference between points A and point C, I see that I now have double the potentials of the individual devices. So I would, in effect, create a voltage. By creating the series arrangement, I would be having a device that gives me double the voltage of a single device. If I look at parallel arrangements now, and again look at the potential difference between point A and point B, I don't pass two different stages. So the potential between point A and B is still phi plus minus phi minus. So there's no additive effect here. So these two devices are arrangements of giving me a higher voltage, in the case on the left of series, or a higher current. So again, remember the internal resistance part. So the device arrangement on the right would allow me to get a higher current for a given voltage. Just for the sake of completeness, if I inverted the directions of the series voltage sources, again, I set the voltage potential at the connecting bar equal, same as before. And however, if I look at the difference in potential between A and B, I still get phi minus minus phi plus, right? And if I look at B versus C, same arrangement. That's the correct arrangement. And if I look at the difference between A and C, I now have a potential of 0. If I look at the measurements for each of those scenarios I had in the previous slide, I have the series voltage sources, I connect them to the meter, and I would get the doubling of the individual sources as I predicted. If I look at the flipped version of that, where I have the two voltage sources plus to plus, then I see how I can get in the circuit a 0 potential. And if I look at this carefully, this is analogous to actually hooking up this circuit, but with both of the yellow leads from the meter going to the bottom of the circuit to the left. So I want to introduce a couple of new terms as regards the circuits. So when I have a circuit drawn as indicated here, namely a voltage source connected to a load here, resistive load, there's no absolute value. In other words, there's no way to define phi plus or phi minus independent of one another. I can only define a difference. So the voltage expressed is strictly the difference between phi plus and phi minus. There's no meaning to this otherwise. And in this case, we refer to the circuit as floating. So it's not, in a sense, anchored to anything. On the other hand, if I attach part of the circuit to something else that serves as a reference, and in this special case, we refer to this as the ground. You've probably heard of this terminology. I'll explain what it means shortly. But by grounding the circuit, I, in effect, define a zero. And in doing so, because phi minus is attached by a direct conductor to the ground, I am, in the principle, assigning 0 to phi minus, so that any voltage I measure on the other side, phi plus, is referenced to a 0 ground. So it's a referencing process. It's a little bit like taking a reference electrode and defining the terminology of the reference electrodes, defining 0 to the hydrogen electrode, and then measuring everything else relative to the hydrogen electrode. I can put the ground position anywhere. So for example, I can attach the ground to the phi plus side of the circuit, in which case I would now set the phi plus is equal to 0, and in so doing I would in effect create a negative power supply minus V. So the idea of ground is sort of common sense. So in the case of natural electric phenomenon, namely thunder and lightning, lightning is a passage of current from a voltage source, namely the ionic that develop inside a cloud formation, a discharge to the earth, which then dissipates the energy. So it's high to low potential. So one states that the earth, the planet itself, serves as a dumping ground for the electrical current in the world and dissipates it. So it is set as a reference equal to 0. So when you attach a circuit to anything connected to the physical planet, Earth, you are grounding it and setting a reference to 0. So in other words, you would set your buildings, you would take the frame of your building, you would ram it into the ground, and that would make an electrical connection, and then that building frame becomes your ground. So in practice, the building has a structural element embedded in the earth. The electrical outlets in the building have a third aperture, which are connected to the structural elements and thereby referenced to 0, namely the ground or earth. And your appliances or instruments have a prong that is inserted into those apertures, and a third wire in the cable or the power out cable is connected to the frame of the instrument, grounding the frame of the instrument so you don't get a shock when you operate the instrument. So just as a final review, I can set arbitrary voltages in a circuit, and there are certain situations in which you want to do this. For example, if you're going to bias an amplifier. Talk about this a little bit later in more detail. So looking at this example, I have a simple resistive circuit attached to power supply B, and then I have the low potential side of the power supply B attached to the high potential side of a second power supply designated as A, and power supply A is grounded. So I have phi minus A referenced to 0. That is set the voltage for the whole system now. If I look at the junction between power supply A and power supply B, the potentials phi minus B and phi plus A are set equal to one another. So in an absolute position, that voltage is now corresponds to, relative to 0, the difference between phi plus A and phi minus A. If I look at the top rail, namely the horizontal conductor at the top of the circuit, that potential relative to ground is the sum of both power supplies. However, if I look at the potential difference across the resistor, it is only the potential difference across power supply B. So bear in mind that the current is not going to flow through power supply A because there's no complete circuit involving power supply A. It's a dead end, in other words. Here's a practical representation of what I've been drawing schematically in the previous slides. So in the upper right-hand corner of the photograph, the black object is a battery. The copper conductor with insulation, white insulation, is connecting a group of resistors. And this is an example of a floating circuit because the only conductive elements, the whole circuit, in fact, just sits in space. There's no absolute potential involved here. And the only meaningful statement about this circuit is the voltage difference between 2 points along the completed circuit. Were I to take one of the leads, in other words, one of the terminals of the battery, and attach it to ground, then I would have a grounded circuit. In many of my lab applications, I'm going to have a power supply that's attached to a wall outlet, an AC source, and through the magic of rectifiers and transformers, it provides direct current DC voltages. We'll talk about this in lectures 3, I believe. So this is the typical box. In the upper right-hand corner are the DC voltage supplies. In this close-up photograph, I have a +5 voltage. I have a variable positive voltage that goes from 1.3 to 15 volts, depending on how I adjust the little dials on the left. And I have a negative voltage, negative 1.3 to -15. Again, if you think about the slides a couple of slides back, you can get a sense of how these are made. The ground is the black plug indicated by the little triangle below the 3 colorful jacks. If I take the same circuit in the previous slide and attach it to the power supply in the fashion indicated, namely the high yellow goes to one end and the low negative goes to the other end of the circuit, I have a floating circuit because there's no referencing. However, if I move the conductor that I attach to the low to the ground, I now have a referenced system. I have a grounded system. And so there's meaning to the statement that the voltage at the first resistor has a positive 15 value. So this is the difference again between floating versus grounded.